We will be starting our session very soon. Some of the participants are still joining, so we'll be waiting for them. In few minutes, we will be starting the session. Good afternoon to everyone present here. My voice is audible to all of you.
Yes, sir. Your voice audible, sir.
Yes, thank you. Thank you very much. So, on behalf of organizing committee, I once again welcome you all to this afternoon session of faculty development program. We are privileged to have with us our esteemed speaker, Dr. Asha Sharma from IIT Roorkee, joining us online. So it is my pleasure to introduce Dr. Asha Sharma, who is currently serving as Assistant Professor in Department of Electrical Engineering, IIT Roorkee. Dr. Asha obtained her bachelor's degree in electrical engineering from HBDI Kanpur, master's degree in high voltage and insulation engineering from Aligarh Muslim University, where she was awarded with the gold medal for academic excellence. She earned her doctoral degree from IIT Kanpur in 2023, where her research focused on interface characterization in nanodielectrics using electrostatic force microscopy. During her PhD, she has also the recipient of the prestigious IEEE DEIS Graduate Student Fellowship. Before joining IIT Roorkee, Dr. Asha served as a faculty member at NIT Jalandhar and Gati Shakti Vishwavidyalaya, Vadodara under the Ministry of Railways. At IIT Roorkee, Dr. Asha is actively engaged in teaching and research in the area of high voltage engineering, insulation systems, and nanodielectrics. Her research primarily focuses on developing advanced polymer-based insulating materials, studying interfacial phenomena in nanocomposites, and enhancing the reliability of high voltage insulation systems used in the modern power equipments. She has published several research papers in reputed journals such as IEEE Transactions on Dielectrics and Electrical Insulations and presented her work at various prestigious conferences. She is also a member of several professional bodies such as IEEE, Dielectric and Electrical Insulation Society, and Indian Society for Technical Education ISTE. So, with this brief introduction, I now invite Dr. Asha Sharma to kindly address the participants and deliver her lecture. I now hand over the session to Dr. Asha. Dr. Asha.
Thank you, Dr. Vishal, for such a pleasant introduction. A very good afternoon to all the organizing committee members and very warm welcome to all the participants. So let me start my presentation. So just a minute, I'm just sharing my presentation. Is it visible?
Yes,
Visible,
ma'am.
madam. Visible.
Okay. Okay, so the topic for this presentation is the condition monitoring of high voltage insulation. That is a key to resilient power systems. So in this presentation, I am going to talk about the resiliency in the power system and what about the high voltage insulation, how is it depending upon the high voltage insulation, and how if we do the condition monitoring of this insulation, how can we improve the resiliency of power system. So I have not included the content slide. So as we with the flow, you will get to know all the contents of the presentation. So let's talk about the grid resilience. So this grid resilience refers to the ability of an electrical power grid to withstand, adapt, and recover quickly from disturbances, right? So when I say the withstand, it means the grid's capacity to endure extreme conditions. When we talk about the extreme condition, actually we are saying the natural conditions, that is the storms, heat waves, lightning, switching operations without significant loss of the service. Means there should be the continuity of the power supply, it should not be lost. The next is the adaptation. So when we talk about the adaptation, this is the ability to dynamically adjust the changing operating condition. Means if there are some changes in the operating conditions, the system must be able to adjust itself. The next is the recover. Means if some disturbances occur within the power system, it must be able to quickly recover from that disturbance and it could restore its normal operating condition. So right now in this throughout this presentation, I am not focusing on this adaptation and the recovery. I will actually focus on the withstand. Let me just use the pointer. Okay, so I will just focus on this withstanding capability of the power system corresponding to the high voltage insulation. So, okay, so we all are aware about the insulation in the power system. So, let me give a brief idea about the insulation system. So, this insulating system consists of the material. So, this insulating material are also called as the dielectric material. When we say the dielectric material, it means a system which is able to store the electrical energy without the flow of the current. That is very, very important, without the flow of the current. But there is nothing is perfect. Always there will be some flow of the current because of few electrons. So actually, we are just trying to compromise that condition that we could restrict that flow of electrons, which are actually present in the system because of the imperfection. So if I talk about the insulating system, we can categorize this insulating system in three categories. That is the solid insulation, liquid insulation, and the gaseous insulation. When we talk about the gaseous insulation, as we all are very much aware about the gaseous insulation, one is air, another is the SF6. So in the power system, if I consider a case of the overhead transmission line, in between the different phases, we are having the same magnitude, but these are out of phase. But still, we don't get any short circuit in between that. The main reason is the air, which is actually present within the phases. So we keep a certain distance in between the phases so that they could not be, there should not be any spark in between them. So again, this air must be serving as a dielectric insulating material. It is a gaseous type. Another is my SF6. SF6 is the sulfur hexafluoride gas. So SF6 is used in the GIS, gas insulated substations. So in the case of the gas insulated substations, where what do I want? The lesser space. So I could accommodate all the power system equipments within certain distance, not in a very broader or the wider area. So we use the SF6 as a gaseous insulation there in the GIS. When we talk about the liquid insulation, very common example is the transformer oil. This transformer oil serves two purpose. It is used for the cooling as well as it is used for the insulation purpose. So when it is used for the insulation purpose, the quality of the oil must be good enough. The reason is in the case of the transformer, we have the windings. Winding must be producing the very high losses. The transformer oil must be able to sustain those high losses. The third one is the solid insulation. Solid insulation is most commonly used, and in most of the cases, we use this type of insulation instead of the liquid and the gaseous insulation. So in the slide, you can see the example of the solid insulation is this overhead line insulator. Other example of the solid insulator are in the transformer oil as well. Apart from in the transformer, apart from the transformer oil, we use the paper insulation in the transformer. The paper insulation is used to separate the turns. And the other insulation, the solid insulation are the XLPE in the underground cable, the cross-link polyethylene. So we can use we can do the part transmission using either the overhead transmission line or the underground cable. In the overhead transmission line, we are having the gaseous insulation free of cost. It's less expensive, but in the case of the underground cable, we have the XLP as a solid insulation, but it is expensive. So these are the categories of the different insulating systems. Okay, so when we talk about the insulating system, there are different properties of these insulating system. When we are saying, okay, let's use this type of insulating system from an overhead line insulator. Let's say in the overhead line insulator, we use the either ceramic insulator or the non-ceramic insulator. So there, those non-ceramic insulators or the ceramic insulator must be able to satisfy certain conditions or certain properties, right? So one of the properties is the dielectric strength. When we say the dielectric strength, means obviously we are talking about the strength of the dielectric material or insulating material. And this is the voltage applied per distance. When we talk about the dielectric strength, means in strength of the dielectric corresponding to a certain voltage for a certain distance. So it is always measured in the volt per meter. If I could take an example of the dielectric strength, the air. So the dielectric strength of air is 30 kilovolt per centimeter. It means if two phases of the overhead transmission line are separated by 1 centimeter, then they can sustain 30 kilovolt, 30 kilovolt voltage. So if we increase the distance, obviously they can sustain more voltage in between them. The next is the dielectric constant. So this dielectric constant is also called as the relative permittivity. Again, the relative permittivity is permittivity means something which is allowing the electric field within itself. So whenever we talk about the dielectric field, we are saying we are not allowing any current flow. Current flow means the charges. Charges must be restricted over there. It means we are saying more and more electric field could be sustained by that. So that is defined by my dielectric constant or the relative permittivity. There is a difference in between the dielectric constant and the relative permittivity. If I say at a particular frequency, let's say if I am talking about the power system at power frequency, it is 50 hertz. So dielectric constant can be said as the relative permittivity. But in a more broader sense, when we go for like into more research, this relative permittivity is actually the function of frequency. So I can say at a particular frequency, the relative permittivity and the dielectric constants are the same thing. But as a function of frequency, we have to say only the permittivity, not the dielectric constant. The next is the dielectric loss. As in the initial slide, I said that this insulating material is something which can store the electrical charge, right? When we are saying it is able to store the electrical charge, we have four types of components. One is my resistance, inductance, capacitance, and the conductance in the transmission line. So let's say if I am saying I am having two phases of this transmission line. So in between this, I am having air. So in between the two phases, the air is present. So it serves as a capacitor. So what we assume that this capacitor must be perfect, means there should not be any leakage across this. But again, perfection are not always there. So we must be having some imperfection as well. There will be some electrons. So we will be having some losses as well, apart from the dielectric constant. So we have to be we must be able to know what is the how many or how much dielectric cost losses could be sustained by my system. The next is the thermal stability. What is meant by the thermal stability? Let's say just take the example of the overhead line insulator. Again, it is not perfect. Maybe there may be the flow of the leakage current. If there is a flow of leakage current across the insulator surface in the transmission line, there will be the I square R losses. If I square R losses are there, means the heat is generated. If the heat, whatever heat is generated is equal to heat dissipation, we will say this is the condition of thermal stability. But if the heat of generation is not equal to the heat dissipation, there will be thermal instability. So when we are choosing the or insulators for my transmission line or for my power system, I take care of this thermal stability as well. The next is the mechanical strength. Obviously, when I am saying the overhead line insulator which are connected to the transmission line, these are exposed to the environment. There will be ice, there will be wind, there will be very stormy weather as well. So whether those insulating materials or the insulator string are able to bear that much ice wind load. So again, it should be mechanically stable. The next is the moisture absorption. What is meant by the moisture absorption is moisture is again the water content. So we all are aware that this water content is a good conductor of electricity. So what do I want? That this insulator must be free of any moisture. If moisture is present, again, transmission lines in power system and the insulators are exposed to the environment, there may be a foggy condition, foggy weather. So again, the material must be able to must be like a non-absorber of the moisture, because I can't avoid the natural conditions. The next is the chemical stability. If I talk about the chemical stability, we can think about this transformer oil. So we are using as a liquid insulating material in the transformer. It is serving as a cooling purpose as well as for the insulation. But let's say some fault occur. Let's say if I am considering some incipient fault occur within my system, within the winding. So obviously, if fault is occurring, there will be some heat generation. So what happens? The oil loses its property. So till some extent, it is allowed that the transformer oil is okay till some extent, but after that we can't reuse it. So that's why we have to take care of the chemical stability of my insulating system as well in context of the liquid insulation or the transformer oil. Next is again the compatibility. Again, when I talk about the compatibility in the insulating system, again the same example of the transformer I can take. Let's say in the transformer, two insulations are present. One is the liquid insulation, another is the paper. When paper is the solid insulation. So whether these two insulating materials are compatible with each other or not, they should not be like in opposition with each other. They must be compatible enough. So this is something we also take care of. Okay, so when we talk about the condition monitoring of the insulation system for the grid resilience, means we are saying my grid should be resilient for some kind of insulating material, but for that I need the condition monitoring. Means again and again I have to monitor the condition of my insulating system so that there should not be the occurrence of any failure of the insulation. So how can I define this condition monitoring? It is a little bit a standard definition. So it is defined as the systematic acquisition and analysis of data from equipment to identify changes in its condition. What was the condition before the fault, or let's say before some disturbances, and now what is the condition after the disturbance? That may indicate developing faults or degradation. Means we are actually trying to see the condition of my insulating material within the power system, so that I could say if it is not attended well, it may cause some degradation or it may cause the development of the fault. So I have to take care of this insulating material. So in this case, what do? We when we are doing the condition monitoring, it is able to detect the incipient faults which are happening at an early stage. Very common example, we can take of the Buckos relay. Again, the Buckos relay is used for the incipient fault detection. So in the same way, we are trying to do the condition monitoring to detect the incipient fault occurring in the system. And next is the prevent unexpected equipment failures. Obviously, if we are able to detect it, we can reduce the failure of the equipment. Optimize maintenance scheduling means what actually happens. Let's say if I talk about the power systems, in the power system we are having several motors, several generators, several equipments which are which we are connected with each other. So in that case, what do? We do the time-based monitoring or time-based maintenance. What is meant by time-based maintenance means, let's say if I am having 100 motors within my power plant, so I will do the condition, I will do the time-based maintenance. Means after 1 month, I will check the all the motors, the rise in the temperature of all the motors that I will do. But if we are doing the condition-based maintenance, maybe we can optimize this thing. Let's say some motors are getting heated very frequently. So I will check according to the condition of the motor. I will check those motors on a priority basis, and other motor which are not being used frequently, and the temperature is also not that much significant. I can just let's say I can just extend the maintenance of that particular motor. So in this case, instead of the time based, we are doing the condition based. So again, there will be the optimization of the maintenance scheduling. Again, it will reduce the manpower. Next is the improved system reliability and safety. Obviously, if there is some insulation failure within the power system, there will be power outages as well. So we can, again, reliability will be improved. Reduce maintenance cost and downtime, the same thing. Okay, so let's say why are we talking about this grid resilience and how it is connected with the high voltage insulation is a very common phenomena that occurred at around in year 2010 was in the NCR region. So what happens during it happened during the foggy weather. So let's say if I am talking about, if you could see, this is the overhead line insulator string. So one of the end of this insulator string is connected to the tower, and this tower is earth grounded. Another end of this insulator string is connected to the line conductor. And this line conductor can be very high as well, 220 kV, 11 kV, 33, or maybe more than that. Okay. So again, all of these are exposed to the environment. So all the dust, dirt, everything is getting accumulated on the surface of this insulator, right? What happened in the 2010, there was a tripping of many transmission line due to the failure of the insulation. The reason was, let's say there was dust and dirt collection over this. Let's say it's okay, no problem. But during the foggy weather, in the fog we have the moisture. So that moist air, the water droplets got deposited over the insulator surface. These dust and dirt particles are conductive in nature. When this water droplets are getting deposited on the surface of this, they become more conductive. Now the surface of the insulator is wet. This is high voltage, right? And this is grounded. So due to this insulator will not behave like perfect insulation. There will be flow of leakage current. The leakage current is again very minute current. It may be in the picoampere maybe or the nanoampere, but there will be a flow of that leakage current. Let's say some current flow across the surface of this insulator. Some current is flowing across this. There is one electrode and there is another electrode. Because of that current flow, I, there will be the I square R losses. Again, we are having insulator. Insulator is not perfect. It may have some resistance. We will be having some I square R. If I square R losses are there will be the heat generation, right? Because of this heat, some of the, let's say this is my the total thing, some of the portion is dried up. If some of the portion is dried up, it gets carbonized. What is meant by the carbonized means whatever is the material of this insulator surface, it will be degraded. If it is degraded, it's the foggy weather. Again, water is getting accumulated. There will be more and more degradation of this insulating surface. If there is a degradation, again, it may cause the flashover in between these two. Because of this degradation, it may cause the flashover in between these two. And this is not something like only one certain type of things. And this is called as a dry band formation. This is not something that this is happening here only. Because of this dust and dirt and the foggy weather, it may happen across the insulator string, and there will be several flashovers. And ultimately, these flashover may occur in the puncturing of the insulator. So when we say the flashover is the like discharge of air, breakdown of air. But when we say the puncture means the breakdown of this whole insulating material, right? So whatever purpose it was serving, it is now useless if puncture happens. So this thing happened during the 2010, and there was there was power outage because of that. So that's why we need to address this issue, that can we take care of our insulating material so that from that insulating side we can say, okay, my grid could be resilient. Okay, so when we talk about the condition monitoring, there are several techniques of the condition monitoring. One is the insulation register, another is the resistivity measurement, dielectric loss measurement, partial discharge measurement, space charge measurement, and the dielectric spectroscopy. There are several other methods as well, but I have included these methods only. So let's say one by one we'll discuss these methods. So first is the insulation resistance. So obviously we are talking about the insulating materials. In the overhead line insulator also we have seen one end is connected to the transmission line, another end is connected to the ground. So obviously it must be able to have a very high resistance to restrict the flow of current. So the equipment which is used for the measurement of this insulation resistance is known as the megger. So this is the diagram of the megger. So in the case of the megger, what do we have? We are having a DC generator. So this DC generator produces some voltage. Mostly it produces around 5 kV. There are two coils in this. One coil is called as the current coil, and the second one is called as the potential coil. So the current coil is producing the deflecting torque, and this voltage coil is producing the controlling torque. So at a balance, this deflecting torque must be equal to the controlling torque, and when this TD is proportional to TC, we will say this V is proportional to I. So if when sign, so I'll have the R is equal to V by I. So in this case, we will be able to measure the resistance. So this is the whole principle of this insulation or this megger. So in this way, we can measure the insulation resistance. So this megger can be used to any power system insulation of any power system equipment to check whether that insulation is healthy or not. There are certain range. The most of the time the range of the insulation resistance must be in the mega ohm. Ideally, it should be infinite. In any power system equipment, the insulation must be of infinite ohm. But again, it can't be. So mostly it is in the mega ohm range. So then next is the resistivity measurement. So okay, so in that case, in the first case we measured the resistance. Now we are measuring the resistivity. Resistivity is again R is equal to rho L by A. So we are talking about the rho. Again, I am taking the similar case of this overhead line insulator, which is connected in between the like in between the ground and the transmission line wire. Okay. So when we talk about the resistivity of this insulating material, whether it's good or not, there are two types of resistivity. One is the surface and another is the volume resistivity. Again, when we are talking about the surface resistivity, we are talking about the flashover phenomena. When we are talking about the volume resistivity, we are talking about the puncture. So both these resistivity matters. So there are certain arrangement that we could measure the resistivity of this whole thing. These are called as one of the method is called as the three electrode arrangement. In this case, we have the arrangement of three electrodes. One is called as this is called as the top electrode. This is called as the ring electrode, and the inner one is called as the guard electrode. So we do the arrangement in such a way, and then we give a high voltage to this top electrode, and other electrodes are grounded, and we connect a certain picometer. Again, we are talking about this insulator, so the current which is flowing across this will be in the picoampere range only. So in this way, we are having the three electrode arrangement, and we try to measure the resistivity of this insulating material. Again, there are some formulas. If anyone wants to know about how do we calculate, we can talk later. There are certain formulas that how can I calculate the resistivity of this, again, the volume and the surface as well, using this three electrode arrangement. Next is the dielectric loss measurement. So as I already said that, let's say this is my insulating material. Ideally, it should be able to store the electrical energy. So ideally, the component correspond to this must be C. But in actual, this is not C only. There will be some R as well. The reason is the free electrodes and the leakage current. So we will be having a C and the combination of R. This we don't know whether these, if I say about the equivalent representation of this insulator string in terms of my RNC, I don't know whether these RNC are connected in series or these RNC are connected in the parallel. They may be in the series or they may be in the parallel. So our main concern is not to measure the C here. Our main concern is to measure the dielectric loss R. So this dielectric loss measurement is also called as a loss tangent or the dielectric loss angle, and it is represented as the tan delta. So this is a primary test for diagnosing the possible degradation. Means if the R is again very low, we will say the material has been degraded. And deterioration of the equipment installation, it may be again this dielectric loss measurement can be done in the factory, it can be done in the laboratory, or it can be done in the on-site, the condition monitoring on-site. And it gives a measure of the bulk losses which are producing under the AC conditions. And these losses are something which we don't want. It also enables the changes in the capacitance to be recorded and can be applied at operating and the test voltage. We also are able to measure the capacitance as well. So very common equipment which we use for the measurement of the dielectric loss is called as the shearing bridge. You can see here, we are having 4 arms here. So let's say if I want to measure the dielectric loss for this insulated string, so this insulating string will be connected in this arm. This Rx and Cx represent the equivalent representation of the it is the equivalent representation of my insulated string, right? This Cn is called as a standard capacitor, and it is a gas fill type. And this R4, C4, and R3 these are the variable resistors. So again, there is a galvanometer which is connected in between two. So at the balance, what should be there? It should show the null deflection. The galvanometer should show the null deflection. So in this way, we can measure the this dielectric loss of this arm, means the dielectric loss of my insulated string or any other insulation used in the power system. Right. So there are several equations. How do we balance them? So at the end, we got these equations. This tan delta is called as a dielectric loss. And this is equal to my omega C4R4. Means this is equal to corresponding to this branch. And in this way, we can calculate the dielectric loss. Again, when we talk about these type of measurements, we have to take care of certain other things as well. Let's say if I'm talking about this measurements, we say this is a shearing bridge. So we say that this R3, the resistor which we are used, which we are actually using for the balance condition, it should be limited to a certain value. The problems again when we are whenever we say we are using some measurement techniques, there are some other unwanted phenomena as well. So one of the unwanted phenomena which is occurring over here is the stick capacitances. So I'm not going into much depth of the stick capacitance. Just for the sake of like clarity, what are the stick capacitances? The stick capacitances are the parasitic capacitances or the unwanted capacitance which we actually don't want in the system. So obviously, if the parasitic capacitances are present here in between the earth and at any metal point to the connection of this shearing bridge, it will affect the accuracy of the shearing bridge. So those must be avoided. And how do we take care of? It's a different thing. We do the electromagnetic, we use the shielding effect and other things. So that's a different story. The next is the partial discharge measurement. This partial discharge measurement is very, very important when we talk about the insulating material. A very common example of the partial discharge is the corona. The corona is called as the partial discharge, which is happening in the air. Partial discharge means, again, it's a partial discharge. Means the discharge is happening partially. If I am having two electrodes, if these two electrodes are completely shorted by some current, we will say complete breakdown. But if these are not shorted by some current, but there is the discharge in between, somewhere in between these two, we say it is a partial discharge. Let's say this is by some insulating material which I am considering. Again, this is some high voltage which I have applied. This system is grounded. You can imagine it's the same thing for the insulator string. So let's say this is my insulated string, high voltage is there, ground is there. If there is if there is something which is causing the partial discharge, it may cause the complete breakdown. How do we have the partial discharge here? Let's say again we are saying these are the insulating material. These may be manufactured by someone. So obviously the insulating material must be having the same property at each and every point. But during the manufacturing, there may be some defect within this. Let's say that the defect may be some foreign particles or it may be some void. When we say some void can be air bubble. Air bubble again, air bubble means it is a bubble of air. Air is having a permittivity of 1. Okay, so one thing I want to clear here is whenever we talk about the insulating material used in the power system, we always are very much concerned about the permittivity or the dielectric constant. If I am saying some dielectric constant is good adapter for that high voltage, means the dielectric constant must be very high. If I talk about the solid, liquid, and the gaseous has the dielectric constant as 1, liquid has more than 1, solid has more than 1 and more than the liquid as well. So if the air bubble is present here, air bubble is having a permittivity or the dielectric constant as 1. The material which we are using here must be having a permittivity more than 1. There is a difference in the permittivity. I have not shown here in the slide if there is a difference in the permittivity in between two materials. The material which is having the lesser permittivity is stressed more. So what happens? At the outside, what am I seeing? Across the insulator string, I am applying a 11 kV. So it must be able to sustain that 11 kV. But due to the air bubble or any defect present in within the insulating system, it may experience lesser it may experience higher electrical stress within itself. Across this, I am saying 11 kV, but within that in string, it may experience more than that because of the difference in the permittivity which are present in the system, and it may break down. So if I am seeing it through the naked eyes, maybe I am not able to see, but after certain time, again and again, if this thing is happening, again and again, the breakdown of the internal void or internal cavity is happening, it may cause the complete breakdown. So if I consider the case of this corona, in the case of the transmission line, this is the breakdown of air. So let's say if you could see, this is the insulator string. One end is connected to this high transmission line. This high transmission line is a conductor. Conductor is a very, very poor insulator, obviously. So it must be having a permittivity much lesser than 1. Around this, I am having air. Air is having a permittivity as 1. This is my insulator, which is connected to this transmission line conductor. The insulator is having a permittivity much more than 1, maybe 10. So there are 3 permittivity reasons. One is 10, one is much lesser than 1, and another air is 1. So because of this difference in the permittivity, the end at which this insulator is connected to the conductor, it is very highly stressed. Means the electrical field is not uniform. It is very, very highly stressed. Non-uniform electric field is present there. Because of that, as I already told, the dielectric strength of air is 30 kilovolt per centimeter. Because of this, the dielectric strength will no longer be 30 kilovolt per centimeter. Because of the non-uniformity, the air may break down at much lesser voltage, at much lesser electric field. So this is called as the corona. The partial discharge is happening. So again, if some breakdown is happening, means we are having the electrical energy. If breakdown is happening, this electrical energy is getting converted into other form of energy. That's why when corona happens around the transmission line, we just see a glow. It may be a bluish glow or it may be a reddish glow according to the polarity of the voltage. Also, we have a hissing sound. If this thing can be experienced in the EHV lines, EHV and the UHV lines. What EHV means extra high voltage, more than 20 kV. It can be experienced very well because this is very common phenomena. The corona is very common in the case of the EHV lines. So what do we want? We want to avoid this. Obviously, if partial discharge is happening here, it will be weaker. It will be weaker, right? Maybe the insulation, this whole insulation may fail and it may not be utilized to its full potential. So it should be avoided. So that's why we use the corona rings over here. But again, till some extent, they provide the protection, but they are not that good enough as well. So this is the partial discharge. It is very, very common. Till the time there are so many research which is going for the detection of the partial discharge, we could overcome this. But still, this is something which is ongoing process. It has been more than 30 years, but the researcher is still doing this partial discharge thing. So when we say the partial discharge measurement, how can I detect the partial discharge? Again, let's say if I am saying this is some my solid insulating material, this partial discharge is within the material. I am not able to see it, right? But how can I measure it? It can be measured according to this. Let's say this is my whole insulating material. So some void or the defect is present here. Again, we are saying dielectric or the insulating material, it is capacitance, completely capacitance, right? If I am not considering the resistance effect. So this measurement is done if there is a if there is a void or something. So some voltage, high voltage is applied across these two terminals, and across, let's say 10 kV is applied here, but in the void, maybe some discharge occur lesser than that voltage. Maybe at 5 kV the discharge is happening. So if discharge is happening, this one and this one are the two walls of the defect or the void, right? So in between the two electrodes, there are two electrodes within the insulating materials. There is a air in between this, so some discharge is happening. What is meant by the discharge? Means obviously some current must be flowing across these two, right? If some current is flowing, how does the current flow? It is the flow of electrons, right? So obviously there will be the flow of electrons. Means there is a flow of charge. So we say in the measurement technique, what do we say? We can measure or we can see this partial discharge if I am able to measure the charge which is getting lost in this during the discharge phenomena. So the whole PD measurement technique is like I am actually measuring the charge lost within this cavity or the void or the defect, right? But again, why this is still not able, why are we still not able to completely avoid this partial discharge phenomena is, let's say if you think of the this transformer, the transformer is huge, the insulation which is used in the transformer is again huge, right? These partial discharge, the void or the cavity are very small bubbles. Maybe if I am talking about something 100 centimeter, in this case, we are just talking about something 1 micrometer, 1 nanometer. So in this huge in this huge insulation system, these things are very, very tiny. So again, the measurement techniques, what we are measuring, we are not sure about whether these measurements are accurate or not because of the uh, difference in this whole thing. Partial discharge is very other reason covering by the partial discharge are very tiny, and the complete insulation system is very large. So that's why it is something that we are still figuring out. How can we detect and localize the partial discharge? One thing I can tell you is like we use the acoustic sensor for the partial discharge detection these days. In the case of the transformer also, if some partial discharge is happening within my transformer oil, so there will be the propagation of some waves because of that, and that those are actually detected by the acoustic sensor. So if the this is the whole body of the transformer, so at certain points we use the acoustic sensors. So these acoustic sensors sense the these propagation of the wave, and that can be detected by the my measurement or the CRO. But again, the accuracy we are not certain about. So this is the whole partial discharge measurement. The next is the space charge measurement. Why am I talking about the space charge measurement? Is the reason is these days we are talking about the HVDC cable. HVDC cable. We should transmit the power at the HVDC. HVDC means so high voltage DC transmission, right? So in the case of the cable, we say that we use the XLP as the insulating material. In the case of the XLP, again, this is the insulation. This is not perfect. It may again have some defect. It may have some voids. It may have some uh, other foreign particles which are present within the system, right? A partial discharge must be happening over there. This space charge, there is a difference in between the partial discharge and the space charge. Space charge means the charge. Let's if I talk about the flow of electrons are everywhere, like they are flowing here and there. But this space charge is the accumulation of charge at certain region. Means we are having a bunch of charge at certain region. This space charge, if space charge is present due to any of the reason within my XLP in underground cable, these space charge produce their own electric field. Let's say if I am having this whole the XLPE insulation in my underground cable, at certain point due to any of the reason, if I am having some accumulation of charges, some positive charges, some negative charges, so these produces their own electrical field, right? So there is one high voltage that we apply across these two electrodes. So these the electric field which is produced by these charges may oppose the electric field produced by this, the voltage applied, right? Or it may go in addition to this electric field. If the field produced by the space charge within my XLP insulation in the underground cable is in opposition with this main electric field, then that's not an issue. But if this in addition with the main field, it causes issue. The reason is, let's say, if I am saying I have applied a 10 kilovolt to for a 1 meter of XLPE cable, so we will say 10 kilovolt per meter will be the dielectric strength of my cable. But if space charge is adding to the this main field, so 10 kilovolt, let's say it is producing, let's say one kilovolt. So this 10 kilovolt will be added to this 1 kilovolt. So now it will be 11 kV. So within the material itself, instead of 10 kV per meter, it will experience 11 kV per meter. So that's an issue. Again, the problem is mostly happening within the HVDC. The reason is, as I already said, this is the accumulation of charges, positive and negative. When we talk about the AC, in the case of AC, we are having two polarity. One is positive, another is negative. So at two electrodes, if this is positive, this is negative, right? So in the next cycle, this will be positive, this will be negative. So whatever is the space charge which is present within the system, it will try to change its position. And maybe when it is changing again and again, I am having positive, negative, positive, negative, positive, negative, it may not cause any problem to the AC system, right? Because of the change in the polarity of these two electrodes, it is also changing its position, right? But if it is HVDC, means the uniform polarity we are having here. So there is no chance of for this space charge to change its position. So it will, if it is in addition with the main field, it will ultimately cause the degradation of the insulating material. So it is very, very important to address this issue. We are also speaking a lot about if we could transmit the power using the HVDC overhead lines. There are three HVDC overhead line till for plus minus 800 kV, which has been in our India. We are also thinking of to transfer the power with more and more HVDC transmission because of the uh, converters, right? So if we are talking about the HVDC, we can't ignore this space charge phenomena. We have to take care of this. Can we design our insulating material in such a way so that this HVDC could be the space charge in this HVDC could be reduced? So that is something which we the whole this space charge measurement. So one of the very commonly used measurement technique for this space charge is called as a pulsed electroacoustic method. So in the case of the pulsed electroacoustic method, what happens? Let's say this is my sample, right? So in the case of this, what will happen? We will try to send a acoustic wave to the sample. So this acoustic wave will try to disturb the space charge, right? Now it will go. Now this wave will be collected at the another end, right? Another end again the acoustic wave. So we will use one transducer. So this acoustic signal will be converted into the electrical signal. So on the basis of this electrical signal, this electrical signal will be the charge signal, right? So this on the basis of the difference in this charge signal, if there are no space charge and if there are space charge, we can say how much magnitude is present of this space charge. Again, this pulse electroacoustic method is used in the laboratories. Right now, we don't have any such equipment which could measure the space charge during the condition monitoring, but the researches are still going on. The very common problem, why don't we use many of the condition monitoring techniques or very good equipments which we actually use in the laboratories, but we can't use in the field, is the noise. If I still talk about the transformer, there are so much noise in the transformer that the proper signal, if I am talking about some partial discharge happening within the transformer, the proper signal could not be detected because of this noise, because that noise used to be get superimposed on my main signal. So again, these all of these are the research things. So again, how do we say that this acoustic wave is equal to my charge? So this is the formula. How do we relate? This EP corresponds to the voltage which is applied to the insulating material. This rho x is the space charge which is accumulated within the insulating material, and this PS is the acoustic wave. So this acoustic wave is related with the electric field using this space charge. So if I am able to know this thing and know this, if I know this thing and this thing, I can easily calculate my whole space charge. This is a equipment which we generally use for the space charge measurement. We just simply put my sample over here, and all of these things are, if anyone wants to know about this, all of this, they can contact me anytime. Okay, so the next is the dielectric spectroscopy measurement. So I already told you this thing that when we are talking about the power frequency, so we say at 50 hertz, we can say dielectric constant, the permittivity are the same thing, but this is not the case. Actually, the permittivity is a function of frequency. At each and every frequency, the value of permittivity will be different. So the dielectric constant obviously will be different at different frequency. So we use the dielectric spectroscopy, and it is a technique which is designed to measure the dielectric properties of any insulating material as a function of frequency. It is used in the high voltage engineering to evaluate the insulation systems, detect aging and defects, and prevent electrical breakdown by understanding material behavior under applied electrical fields. If I say about this overhead line insulator, if I am saying the EHV transmission line, let's say some 230 kV, then these insulators are in the stress of 230 kV for a very longer duration. So we actually just want to know if something is stressed so much for a very longer period, how the material properties are getting changed. So that on the basis of that, we could decide something else as well. Means we could think of some other insulating materials as well, which could be sustained for a longer duration, so that we could prevent our insulation failure. So the dielectric spectroscopy measures the interaction of an external electric field with the electrical dipole moments in the sample. I am not going into much depth with this. You can just think of this thing like when we are saying dielectrics. So how do they store the energy? The reason is the dipole. Let's say when we say the what are the dipoles, we say that the current is due to the flow of charges. Charges means the free charges, but apart from the free charges, we are also having the bound charges, right? So bound charges means they are still bounded to their atoms or molecules. Now they are separated by some distance, right? So they form a dipole. Because of that dipole, we have the polarization. This polarization is actually responsible for the insulator to be a insulator. If I am saying insulator is a bad conductor of electricity, it is because of those polarization phenomena, and it is because of those dipoles and the bound charges. I am not going to much depth of this. So we say, okay, so this is something you must all know. D is equal to epsilon naught E. Means the electric flux density, if I am applying a voltage across some equipment, this D will be equal to epsilon naught E. But apart from this, if I go into much depth for this insulating material, apart from this, there is a P also. P is called as the polarization, right? So this electric flux density will be equal to these two things. And how this polarization is affecting the whole insulation, that's a different story. But these polarization, if you could think of something, your 12th physics, there are several types of polarization phenomena. The ionic, atomic, molecular, and the interfacial type of polarization. And this permittivity corresponding to the electric field and the voltage is affected by the polarization which is happening within my insulating material. Okay, so when we talk about all of this, okay, so I am saying, okay, I am doing the condition monitoring. I am using the same insulating material everywhere. Means obviously, if I am talking about the transformer, in the transformer, I have transformer oil, liquid transformer, again paper insulation. In the bushings also, I am having some insulating material, let's say silicon rubber or the epoxy. But the same thing, but still I am experiencing so many problems. So how can I overcome the challenges which I am experiencing in the condition monitoring? So I can think of, okay, let's say in the power system equipment, this high voltage is there is like high voltage. We are just increasing our voltage level so that we could reduce our losses. But if we are going for the higher voltage, we have to have the very good insulating material as well, right? We can't think of condition monitoring all the time. So how can we address this issue? So this issue can be addressed by changing the insulating material. So right now we are having the insulating material epoxy, silicon rubber, porcelain, mica. Can we think of something else as well? So yes, we can think of something as well. One is the nanodielectric, another is the functionally graded materials, third one is the self-healing materials, and the fourth one is the biodegradable materials. I will just talk about the nanodielectrics and the functionally graded materials, but little bit about the self-healing materials. Self-healing materials are those insulating materials which could self themselves. If I could give you an example, is the self-healing insulating material is my air in between the transmission line, right? The corona is happening over there, right? Air is ionized, the breakdown of the air is happening, but I don't need to replace the air. Air is still there, right? Again, it is free of cost. So this is my self-healing type of material. But apart from air, can we think of some other insulating material which are also self-healing, so that I don't need to replace them? They could self-heal themselves. So again, it will, if they are able to self-heal themselves, there will be lesser failure of the insulators. There will be more resiliency in the grid. There will be more resilience in the power system equipments we can think of. The fourth one is a biodegradable material. So these days we are talking about the sustainability. One thing, the transformer oil, the liquid insulation, the very, very major problem with the transformer oil is we can't dispose it. It is hazardous to the environment. We can't dispose it. So we are thinking of something else. Instead of the transformer oil, can we use some other oils as well? Still, we are using some vegetable oils, some mineral oils, but those are these are not that good enough, and they have not been commercialized yet. So can we think of something else which is biodegradable also? Means after the use, we can uh, these are actually, these are not hazardous to the environment, right? So right now I will just focus on the nanodielectrics and the functionally graded materials little bit. So what are the nanodielectrics? Very simple thing is, till now we are using the insulating material. Let's say the overhead line insulator, I am using only the silicon rubber or the porcelain, right? This is one material only. So can I use something else as well within this material so that it could enhance its electrical properties? The permittivity could be improved. The voltage, if I am talking about the higher voltage, if I am thinking about to go beyond 765 kV in India, I think 1000 kV or more than that, we have to design some insulating material. So can we do something with that? So that one, the nanodielectrics, in the case of the nanodielectric, if we are having a simple material, we use some nanoparticles. Again, its name specifies it is nano. So obviously the dimension of the particle, which are these green color, these are nano, around 40 nanometer, 50 nanometer radius only. So what do we think of, like, let's say I am having some this silicon rubber, the insulator, which I use in the insulator string. I have used a nanoparticle. So what do I think? It will be like a simple mixture, just the nanoparticle or this matrix, but this is not. What happens? Apart from this, apart from this matrix and the nanoparticles, I have something else as well. This is called as the interface. So this interface, it has been seen, if it has been seen that the partial discharge, which is which is a very problematic in my power system when I'm using the insulation, the partial discharge characteristic improves if I use the nanodielectrics. It has not been commercialized yet, but it has been seen when we are doing the laboratory experiment. It has been seen that the partial discharge activity has been improved little bit if I use the nanoparticles. And then this interface is actually responsible for the improvement. This interface has the characteristics completely different from this matrix as well as from this particle. And this is again some nanometer in dimension. So the reason behind this, as we are reducing the size of these particles, this interfacial region increases. If this interfacial region increases, it is responsible for the improving properties of my insulating material, which could be used in my power system equipments or in my power system, right? So there are several models which have been available for this nanodielectrics. One of the model is very, very popular is the Tanaka's interface model. I am not going into much depth of this, but I have worked on it. I have worked on this interface model, and I have also seen that apart from when we are mixing two dielectric materials, one is nano, then properties used to get improved, and there is an interface as well. And this interface has some different properties which are literally different from the matrix and the this nanoparticle. If anyone want to know about this, they can ask me after the session. Okay, so how are we saying that the how is it improving? So very common thing which we have seen till now is like, let's say if I am just using some epoxy for my insulation, the power system. If only epoxy is there and some high voltage has been applied, there will be the erosion of the epoxy over here. But with this, if I use the nanoparticles, if you could see where the nanoparticles are present, they are at the beneath of that nanoparticle, at the bottom of that nanoparticle, there is no degradation of the material. Here as well, there is no degradation of the material. Here as well, there is no degradation of material. The only reason which is degraded is the material which is in between these two. It means if there was no nanoparticle, the whole thing will be eroded very easily, very early. But if the nanoparticles are present, these nanoparticles provide the hindrance for the degradation and for this erosion, right? So again, this is good for my power system. The failure will be less because of this material enhancement. The next is the functionally graded composites. It's the same thing with the nanodialectics, but in the case of the nanodialectic, we are saying that if we are having some base material, we are mixing the nanoparticles and it should be uniformly mixed. But in the case of the functionally graded, we say no need to mix them uniformly. Let them uh, mix in any other way as well. So this thing has been said that the functionally graded according to the function. Can we grade my nanodielectrics? Right. So how can we define the functionally graded composites are the advanced material? These days still some research are going on. I am also working a little bit on this FGM. I am working on this overhead line insulator. So the same thing which I have discussed with you, like partial discharge at the end of the insulator strings, right? So the electrical stress is very high. So I am also working on this. Can I use some FGM over at these ends so that I could reduce the partial discharge, so that I could enhance the characteristic of my in the insulator string. So these are called as the advanced material, where composition or structure gradually changes over a specific dimension, resulting in tailored properties, modified properties within the material itself. Right. So it has been shown FGM has not been used till now. Most of the time, it has not been used in this overhead line insulator. It has been used in GIS, gas insulator substations. So this it has been shown that the instead we are having the different mixture of these particles, if I could say. In the case of the nanodielectric, these are uniformly dispersed, but here we are not having. So the properties also changes gradually. There is no drastic difference in between the permittivities. There will be the gradual change in between the permittivities, in between the characteristics of the properties. So these functionally graded composites can be used at many places. Um, these can be used in the energy conversion devices, switchgear component, nuclear power plants, some of varied coatings, bushings, cable, and terminations. It can also be used in the high voltage insulators. So mostly the hot topic is like, how can I use this? How can we use this high FGM in the high voltage insulators? So main thing is like the thing which we are thinking of is like, can we little bit the thing which we have discussed is the permittivity, right? So if the permittivity is high, it is a really very good insulating material. It can sustain that much very high voltage till the 765 kV, right? But apart from this permittivity, we are also concerned about the conductivity as well. The reason is these insulated strings are exposed to the environment. So one end which is connected to the conductor, another is grounded, right? Exposed to the environment. So the conductivity will also be there, which case I have also discussed the tripping of the transmission line because of the dry band formation. So it will also be there. So conductivity will also be there. So can we balance these two, the electrical conductivity and permittivity, so that we can reduce the electrical stress at the end of the this high voltage insulator string? A little bit we could contribute to the power system community. So again, when we say the too low dielectric permittivity, breakdown will be very early. If we say the too high dielectric conductivity, there will be the surface flash over the charge accumulation. So we have to optimize little bit these electrical properties for which could be best for the long-term HV high voltage insulation performance. So how can I summarize this whole presentation? I am going to end this presentation is this condition monitoring plays a crucial role in maintaining the reliability and resilience of our system by preventing insulation related failures. Mostly all of the time I have just talked about the insulation related failures, and it is very important. You can't use power system equipment, or you can't use your power system without the insulation. It is very crucial. You can't use. So you have to take care of your insulation as well. So, and it also enables the early detection of insulation degradation mechanisms such as aging, moisture. It utilizes multiple diagnostic techniques, which we have discussed, like dielectric loss, partial discharge, insulation resistance testing. Also, it supports a transition towards smart grids and integration of new insulation technologies like the nanotechnology, nanodielectric, like the functionally graded composites, like the self-healing dielectric materials, like the biodegradable materials, right? Also, if with the ongoing innovation, wider adoption and standardized protocols, it will be crucial for future improvements in the power system resilience. Yes, of course, it will be very crucial if we are able to do any of these things, which could improve the insulation performance. So obviously, it will boost the power system resilience. So this is all from my side. Thank you for your attention. If there is any question, you can ask me.
Thank you very much for your excellent and insightful presentation. So now I request participants if they wish to ask any question or they want to interact or discuss something related to this topic. Participants, they can unmute yourself and they can ask if they wish to ask something or they have any query. So
You can also ask me later as well if you think of something and you want to share it with me. You are most welcome via email as well.
So later on also you can ask the question, or if you have any query later on, you can ask through email also to her. So thank you very much. So your talk has provided us with valuable understanding about the insulating materials, properties of insulating materials and practical perspectives that will surely benefit our participants. So on behalf of all the participant and the organizing team, I extend our heartfelt thank you uh, for
Thank you,
your
Dr.
valuable
Vishal.
time and sharing your knowledge and experience. So, with these words, I formally close this session for today. And tomorrow we'll be meeting for next session at 5 p.m. So, all the participants, thank you. Thank you very much. Thank you to Dr. Asha Sharma. Thank you.